Okay, eruptions and the time between eruptions and the length of eruptions. Okay, complete 8 and B. Does the residual plot confirm that the relation is linear? Okay, let's click the, well, let's always click the scatter plot. So does this look pretty straight? Does this look like a pattern? Yeah, to me that looks like a very strong pattern. Nice and straight. Look at the residual plot. So does this look straight? Enlarge it a little bit. Well, let me ask, do you see a U pattern or anything? I don't really see anything. I mean, it's hard to tell because the vertical scale is so compressed, but there's no big obvious swinging U or upside down. There might be a little bit of an upside down, but I'd say it's not really obvious. So I would say the plot of the residuals shows no pattern. If it shows no pattern, that's the Cheerios plot. The model is fine. Okay, let's continue. The coefficient of determination. So that's something we haven't talked about. So let me just tell you what it is. There are different ways of measuring how closely x and y are tied to each other. So we have two variables, x and y. One way is the correlation coefficient. The other way is the square of that. Now, for some reason, when we square it, r squared, most people write it with a capital R. I have no idea why. This is the percent that's explained. So we have a lot of explaining to do as to why the points vary up and down. The coefficient of determination, which is the square of the correlation, tells us how much is explained. So here it's 95.4%. That means it explains 95.4% of the pattern. So the least square equation explains 95.4% of the y, the length of eruption. Percent explained of y. So this is extremely high. We've explained 95% of the variation. A lot of times we would be happy with explaining 30, 40% if the numbers were really variable. Okay, so coefficient of determination is the percent of the variation in y, because we're always concerned about explaining y. Okay, so that was 13.